K5. Let's check off some basic things, right? So first of all, K5 is definitely simple. It has 5 vertices, so the number of vertices is bigger than 3. It's very connected. Right? And let's just see how many edges and vertices and how that inequality works. So we're curious, this last point here we need to check is e greater than 3b minus 6. Alright, so K5 has 5 vertices of degree 4. Make sure that makes sense to you, right? It has 5 vertices. Each vertex is connected to 4 other vertices. And so the sum of degrees is 20, so it looks like E is 10. 5 vertices, so let's see, it's 10 greater than 3 times 5 minus 6. 15 minus 6 is 9. Yep. Right, so since all of these are checked, not planar. Okay, let me show you a little sketch that is not an argument for not planar. It's just another failure of being able to draw the thing without edge crossings. But it kind of helps you get a feel for the theorem a little bit. It's the only reason for doing this. Okay. So what you can do is you can kind of make a best attempt at drawing this thing without edge crossings. And here's one of my favorites. I don't know, it's sort of some variant of this. And here's kind of what's happening. So this is okay. This is a planar graph. It's not K5, but it is a planar graph, and it has 1, 2, 3, 4, 5, 6 faces, right? And we know that it also has 5 vertices, and I think I have 9 edges. Double check that, but I have 9 edges, and face count is 6. All right, so 1, 2, 3, 4, 5, 6. 5 minus 9 plus 6 is 2, right? As it should be. Should be 2. So far, so good. Alright, so what's the task to complete this? Well, to make this K5, I have to add one more edge, right? So I would have to go from 9 to 10, and I don't get to change the number of vertices. So this means that the number of faces would have to go to 7. I'd have to do this by only doing one more face. Okay, because it has to stay at 2. If you're going to add one to the edges, you're going to have to add one to the face count. And what I have to do is somehow I have to connect this vertex to this vertex. And I can't do it for a lot of reasons, but one kind of intuitive thing is you can kind of see there's a structural problem in getting this done with only one face. It seems to be forced to interact with 2 faces and cut those faces into 2 or something. Right? You are stuck and you just can't get this done. And it's simply because of face degrees. It's actually this inability to mess with the faces in this way that really gets you stuck. Okay. Now, if this was on a torus, did this in the problem session, it would have been today, but I know you watch videos different days than problem sessions. If you had a wormhole, you could do this. Right? So, boop. Dunk. Ta-da! Okay, now this is not a sphere anymore. This is a sphere with a wormhole on it, which is actually this. It's a sphere with a wormhole. It's not a very good wormhole because it requires it to travel really far. But you could think about kind of tightening up this handle and having more bend in the sphere to make it a good wormhole. But anyway, that's kind of where we're going with this a little bit. We can see we can't do this on a plane, but with a wormhole we could. And yeah, there's just a lot of problems with this, but it's a fun doodle problem to have. Okay, so think about K5, right? It obviously doesn't work, has too many edges. Let's try this with K33. Okay, it's another one that's very important. Remember, this one we don't mess with as much, it seems, but it's the complete graph, complete bipartite graph with 3 vertices in every group, and has all the connections across groups possible, making it complete, at least from a bipartite sense. It is not K6. Right? K6 is a different graph entirely. It has more edges than this one does, because there's connections within groups if you want to take the bipartite view, which then it wouldn't be bipartite, right? Okay, let's see, is it simple? Yes. Definitely connected. Definitely at least 3 vertices. Let's check the edge and vertex count. Okay, so I have 6 vertices. 6 vertices of degree 3. That's 2e, so there's 9 edges. Okay, 3, 3, and 3, 9 edges. Alright, is 9 greater than or equal to 3 times 6 minus 6? 3 times 6 is 18, 18 minus 6 is 12. No, right? So does that tell you K33 is planar? No, it does not. It doesn't tell you anything. This theorem just doesn't apply to K33. You have to get all of these things checked before you can make the conclusion, not planar. There are lots of graphs that fail to have too many edges and still are not planar. K33 is just one of the first ones we see, but that happens quite a lot. You really need to get a lot of stuff going on before this thing really kind of applies. It's not going to apply every time. All right, so we don't have to like give up. The thing is, we can make a similar argument here, and there is a version for bipartite graphs of this too many edges theorem. And here's what we have to adjust. All right, so bipartite graphs with at least 3 vertices do not have any odd length cycles. So they don't have any cycles of length 3, so they can't have any triangles, for instance, or odd degree faces. And they're not going to have any cycles of length 1 and 2. This is a property of just bipartite graphs in general, so you don't need the b greater than or equal to 3. Bipartite graphs just don't have any odd length cycles. But when you start adding b greater than or equal to 3, this means that you have no faces of degree 1, 2, or 3 that are possible. Boy, that's really legible. 1, 2, or 3 that are possible. My handwriting's gotten really bad during this pandemic. There we go. Okay. A degree 3 face would have to have the structure like this. There would have to be a connection within a group to pull this off. And you know this can't be done, right? It has to go back, forth, back, forth. So they're all length 4 or greater. So this means that 2e is at least 4f. All right, and so you get f less than or equal to 1/2 e. b minus e plus f is equal to 2. Solve both for f. 2 minus b plus e. Connect these two together. And if you just want to do it yourself, you can. But e is less than or equal to 2b minus 4. So bipartite graphs are a little more constrained with their number of edges than regular ones are. Sorry, not regular, I should use than just general simple graphs. So when you have a bipartite graph, it can't have as many edges. And that's a good thing, because otherwise we wouldn't have a tool for K33. So we're going to check to see if e is greater than 2b minus 4. And it is here. So e is 9. We have 6 vertices. 12 minus 4 is 8. Okay, so add 9 is greater than 8. And there is something that you might start to notice a little bit. It's not a lot of a pattern, but it seems to be the start of one. And that seems to be 10 is greater than 9 is like the first violation of this one. And 9 is greater than 8 is like a first violation of this, right? It seems like if right, otherwise, right, it wouldn't work, right? 8 is not greater than 8. So I got my head a little bit there. So these two actually are the breaking points for where graphs become non-planar, but it doesn't seem like it should just be two graphs. It seems like it should just be like an infinite family maybe, or something more complex. Turns out no. K5 and K33 are really that boundary for planarity. Kind of in a looser sense than exactly these two graphs, but there's a process called contraction and subdivision, kind of inverses of each other, that help us relate graphs to K through 3 and K5. Okay, so what we're going to do in the next one is we're going to look at some other properties of planar graphs. I want to talk about regular planar graphs, Platonic solids, which are important, and then we're going to start kind of incorporating these ideas together and start talking about the broad picture. How do you tell if a graph is planar or not? If it is planar, you just have to draw the edge crossings, right? So that's fairly easy. But how do you tell if a graph is not planar? What tools do you have in your toolbox? And that's going to be the purpose of our further discussion here, is to expand that toolbox to be as large as possible. And we're going to do that next with Platonic solids, which is it's an interesting topic just in its own right, but it also expands your toolbox of what you can do with planar graphs and what you know is possible and impossible. All right, so I'll see you in the next one.